So let's look at a concrete example in R Studio. So here, what I'm going to do is I'm going to run a regression. The response variable, continuous response variable here is income measured in $1,000. And here we have three covariates: age measured in years, female, right, a dummy variable with one coded as female, zero coded as male, and education measured in years of education. And the data we use is use and DTA. Well, after data management and cleaning the steps. And here, the regression model might not make a lot of sense, but what I'm trying to do is to illustrate how to provide interpretation of the results from a typical linear regression model. So here we can run the model, right? We can hit the run button here, and we're going to see the results here in the console. Right? And so here for interpretation of the coefficients, so let's begin with the intercept. So intercept is equal to 24.61443. What is substantive meaning of this intercept? Well, we say while holding all covariates to be zero. So when all the covariates are zero, we would expect what? Expect the Y. The Y is income measured in $1,000, right? So we would expect the predicted income to be $24.61443,000. So in this case, this is interpretation for intercept. Now let's go to go through the rest of it. For the slope estimate for age, okay, age. So this is negative number, right? And be careful about direction association. So in this case, we're going to say, well, first of all, we have to clear it off, right? We have to say begin with holding all other variables constant. And that is the beauty of doing multiple regression. That is, we can hold all other variables constant. That is, holding the effects of all other variables certain level, right? We would expect for each year increasing age. So that is 1 unit increasing age. We would expect the income to what? To decrease. Why? Because the sign in front of this estimate is negative. To decrease by what? $0.54000,000. So in this case, roughly $540 for each year increasing age, right? And how about this dummy variable? Well, dummy variable is a little bit tricky, but still we're going to say, well, holding all other variables constant, being female as opposed to being male is going to what? Increase or decrease? Well, because the sign in front of this estimate is negative. We're going to say, well, for it being female as opposed to being male is going to decrease one's income by what? $6.8086 Okay, so roughly, females get $6,810, roughly speaking, less than that of males. What about education? Well, similarly, okay, similar to interpretation for age, we're going to say, well, holding all other variables constant for each year increase in education. That's how education is measured, right? We would expect income, predict the income to increase. Why increase? Because the sign in front of this estimate is positive, right? Income is going to increase by $3.61544,000. Why? Because the income variable is measured on a scale of $1,000. Now let's scroll down. Let's look at R squared. So here R squared is 0.2623, meaning that, right, 26.23% of the variation or variance in income measured on $1,000 is explained by our model here. Okay? Of course, we have standard errors for these estimates, t-values for these estimates, and p-values. Usually, when the p-value is smaller than or equal to 0.05, or smaller equal to 0.05 for the p-value, we say its corresponding what? Estimate is statistically significant, meaning that its corresponding variable has a statistically significant association with the response variable here. Well, in this case, looks like all estimates are statistically significant, right? And that would imply age, gender, and education all are statistically significantly associated with the response variable income.